Yeah, so I'm thinking, well, I'll do day 17. Let me hit refresh here because 17 is unlocked. And then if I can finish 17, I'll go back to 16. I just want to keep up with the current day. And then, as I said, 16, I was told, is hard, so I don't want to get too bogged down. It's a weekend stream. I don't get a chance to do it very often. But let's take a look at 2022, day 17, Pyroclastic Flow. Your handheld device has located an alternative exit from the cave for you and the elephants. I'm going to guess the elephants was something that we encountered in day 16. Because that came out of nowhere. The ground is rumbling almost continuously now, but strange valves have bought you some time. It's definitely getting warmer in here, though. Tunnels eventually open into a very tall, narrow chamber. Large, oddly shaped rocks are falling into the chamber from above, presumably due to all the rumbling. If you can't work out where the rocks fall next, you might be crushed. 5 types of rocks. Okay. So we're doing Tetris. Tetris in a volcano. The rocks fall in the order shown above. First the minus shape, then the plus shape, and so on. Backwards L, the line, and then the square. Okay. All right. So once the end of the list is reached, the same order repeats. Okay, that makes sense. Right? We're just doing that. And then rocks don't spin. Oh, okay, that's good. But they do get pushed around by jets of hot gas coming around out of the walls themselves. A quick scan reveals the effect the jets of hot gas will have on the rocks as they fall. Your puzzle input. For example, suppose this was the jet pattern in your cave. Let's save that as test input. And then let's also get our regular input. Get input 2022 17. Whoa, one line, but it's a very long one. Okay, lots of jets of gas. Wiku says 16 was really hard. Took me basically half the day. All right. So maybe I won't be able to do it after I finish 17, assuming I do finish 17. All right, jet patterns. Left means a push to the left, while right means push to the right. Okay, that makes sense. And it's just lefts and rights. The pattern above means the jets will push a falling rock right, then left, then left, and right, so on. Okay, so I think I get it. I understand what's going on here. A tall vertical chamber is exactly 7 units wide. Each rock appears so that its left edge is 2 units away. I'm looking right here. From the left wall, and its bottom is 3 units away from the floor. Or above the highest rock in the room. Okay. After a rock appears, it alternates being pushed left by being pushed by a jet of hot gas 1 unit, and then falling 1 unit down. If any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move onto a floor or already fallen rock, the fallen rock stops where it is, having landed on something, and a new rock immediately begins falling. Okay. So only downward movement, the way I'm reading this, only downward movement will stop the rock. If you do a jet into a rock, it won't stop the rock. The rock can continue to fall down. Drawing a falling rock with @ and a stop rock with #, the jet pattern in the example manifests as follows. Okay, and then we have, oh, okay, is he going through like the first few rocks? Yeah. Wow. Okay, so what are we trying to do? To prove to the elephants your simulation is accurate, they want to know how tall the tower will get after 2022 rocks have stopped, but before the 2023 rock begins falling. In this example, the tower of rocks will be 3068 units tall. How many units tall will the tower of rocks be after 2022 rocks have stopped falling? All right, we got our puzzle input already. Let's create our file. I'm just trying to think of how we want to do this. What I can do is just model the rocks, the Tetris pieces, as just bits. And that way I can use ands and ors to move, to test, that kind of stuff. I'm not doing day 16 yet. Let's do day 17 instead. 17. And I'll put 16 in when it's time to do 16. Yeah. I couldn't stream yesterday, so I haven't done that one. Let's build a file. Let's create it. Let's generate this thing. Let's run bacon. Let's make sure we're running day 17. There we go. Okay. 2022, day 17. So parsing is going to be simple. Jets, let's call it vec of char, I guess. I could always convert it into an enum, but that seems like overkill. So self jets is equal to aoclib. I think it's called read to chars. I think. Let's find out by printing out the length of the jets. Let, oh no, self jets len. $41. Okay. Now we need to model a cave. This is a cave or a pyroclastic chamber, or what are we talking about? Yeah. Oh, we exited from the cave. I'm just trying to see. We got tunnels. So we got a narrow chamber. Okay, let's call it a chamber. Struct chamber. We can initialize it with, I guess we could just copy the jets. There's no reason to stick them in there. Maybe that's what we put in here is the chamber. And then clone it for part 2. Yeah, chamber. But that also means we need to derive default, because my struct derives defaults. So the jets is going to be the vec of chars. And so you can just say that here, self chamber jets, vec of chars. And then what else is in the chamber? I guess we can just create the tube. The tube of rocks is just going to be a vec of u8. Right, because these are it said it's seven bits wide, right? So we can just ignore the eighth bit, the sign bit, right? In fact, we can print out a little thing. We can make a little chamber printer, chamber printer, and then we rotate among the pieces. Okay, so the pieces are going to be and we also, the end of the list is reached, it repeats. It says it right here. So I guess what we can do is keep track of what jet num we're on. And then impl chamber. And let's just create the pieces. The pieces will just be, I guess, just a 4x4 grid. Oh, you know what we could do is we can make it so that they're basically this, right? Okay, let's do that. So if I say it's U8 4, and how many pieces? There's 5 pieces. We can just create bit masks for each piece. So the first piece, let's make this the bottom. So 1, 2, 3, 4, 5, 6, 7, 8. I think those are, it doesn't matter how many zeros actually, but it does matter here. So it's going to be 2. Oh, it's only 7 bits wide. Okay. You know what we can do is just make these all 7 bits. And that way I can say 0, 0, 1, 1, 1, 1. Right, it starts here at 0. Oh. Yeah, that'll work. We get just 7 bits. And now for this next shape, the first row is going to be blank. The second row is going to have 2 over, 01, and then like that. The next one is going to be 2 over 1, 1, 1, and then 0, 0. And then this one is the same as the second one. Okay. This piece is going to have 1, 2, 1, 2, 1, 1, 2, 1, 2, 1, And then 1, 1, 1. So it's the same as that one, right? Oh, no, I want to start off at 0. There. Almost made a mistake. Fatal error. And this is very simple. This is 0, 0, 1 repeated. Like that. And then the final piece is going to be 2 zeros. And then 1, 1, 0, 0 repeated. Like that. So I think these are the pieces. Let's do a fn print piece. And we'll just give it a piece. U8. I just want to see that how it looks, if these look right. CodeMonk, hello. CodeMonk says, hello, Uncle Scientist. Good luck with the problem. Thank you. This seems like it's going to be pretty complicated because we have to basically implement Tetris. So let's see how this goes. Let's see. So OX80. Oh, we're going to do for each line for P in piece, like that. And then we can say while bit is greater than 0, print bang this if bit and P is not equal to 0. Then we're going to print a hash. Otherwise, we're going to print a dot, right? And that's all we need to do. And then shift the bit shift by 1. And that's going to print out a piece. So let's see if we can do that in part 1. We can print out all the pieces. For piece in chamber pieces, chamber print piece. Oh, is it already a ref piece? And then println just to separate them out. And let's see what that looks like. Did I get the pieces right? Ooh, I got everything wrong. Oh, deriver. Oops. A vec of char. Oops. Self jets. Oh, self chamber jets len. Computing. Uh-oh. Did I mess up? Oh, no. Well, that looks all wrong. Oh, because I forgot to do this. Println. Oh, right. We actually want to start at 4. Yeah, so there's 1 dot on that side, then there's 2 dots on that side. Right, okay. I think we got the pieces right. What do you think? That looks right, and they all start 2 to the left of the left wall. Perfect. All right, so the next thing we need to do is figure out how to drop a piece, right? We got to put a piece on in our rocks vec. I guess we can start the rocks vec off. We can start it off with a few. Yeah, let's create a new. Actually, what we can do is let's do it this way. Jets is yeah. Clippy's going to tell me to do it this way, isn't it? Self. Even though I want to do it the other way. Actually, you know what we can do? We just pass it in. Right? We should be able to do that. And then just say self jets. Just put it in there. Rocks is going to start out as a vec of, we're going to just throw a few empty rows. That way we don't have to worry about initialization and figuring out if there's enough space to put stuff. Piece num is going to start at 0, and jet num is going to start out at 0. And those will increment as we go through. And then we can say self chamber is equal to chamber new. Let's see if this works. I broke something. What did I break? Oh, I put a semicolon there. Okay. Expected. Oh, right. I have to map them to. Oh, yeah. It's supposed to be char. That was a dumb mistake. All right. It should still print out the pieces. Good. All right, so we can stop printing the pieces out now. And I think we have a decent chamber. And now we can just say drop piece. I guess one thing that'll help is if we have a thing that says draw self. And we can just draw out what the chamber looks like. We need to start at the top, which is going to be the last one. Self rocks len -1. And while top is greater than 0, and we want to draw one line. So I'm going to draw it the same way they've got it here. So print bang with a vertical bar. And now we'll take a look at the rocks row. And it's basically this thing here. This one line. Let mut bit. So I might be able to extract this out. While bit is greater than 0, print bang this. Right? Let me extract this out. Fn print line. And it's just basically we just taken a U8. Let's call it a row. Row U8. And it's just this code here. And I can just say print self print row p. All right. And then here we do the same thing, self print row self rocks top. Then we say println this top minus equals 1. We're done. Oh, we want to actually print the 0th row. So let's do it this way. And then we'll print out at the end plus 1, 2, 3, 4, 5, 6, 7 and a plus. Okay, so let's see if we can draw the chamber as it is as soon as we create it. So we can just say self chamber draw. Let's see what that looks like. That failed. Does it matter? I mean, passing the reference to a U8 or copying it, it just means I have to put stars everywhere I want to use it, but I can live with that. Oh, and then I called it P instead of row. Here. Okay. Okay, so we have an empty chamber, which is what we were expecting. Okay, so if we want to put a piece in the chamber, let's create a function called drop. Drop one. And then we can just call this repeatedly, not self. So how do you drop a piece? Our current piece, the piece that we're going to use, is coming from self pieces of self piece num, right? And then we want to increment piece num, self piece num. Oh, I can't just say plus equals 1 because it has to rotate, right? So it's just self piece num plus 1 close paren, which I'll fix in a second, mod self pieces len. That way if part 2 says, oh, there's 5 different more pieces, but I don't have to change this code. All right, I do want to call drop 1 and then draw the chamber. Self chamber drop. Oh, that's right, I was going to clone it. So let's do that now. Let part 1 equals self chamber clone. And I think I'll have to add clone to it. Part 1 drop 1. Part 1 draw. And I think I just need to derive clone and I should be good to go. Computing. Here we go. A bunch of warnings because we're not using it, but nothing's broken yet. Okay, so now we've chosen the piece. Let me try just slapping it in there. We need to start it off at the height of the thing. We don't know how to compute the height, but it's supposed to be 3 up from the whatever the top row of rocks is. Right? So we do need to compute the height for the answer, right? That was what the answer was asking for. How many units tall will the tower of rocks be? So we at least need to know how to do that. So fn height self. That'll be u size. Let mut top is equal to self rocks len while top while self rocks top mut -1. Jose Farbin, thank you for the raid. Very much appreciated. Welcome. Okay, while self rocks top -1 is equal to 0, right? If there's nothing there, then we'll just drop the top by 1, and then just return the top, and that'll be the height of our chamber. All right, so now that we can calculate the height, we can get the height that we're going to put the piece in, and we need to make sure that the chamber of rocks here is going to be big enough to just slap a piece in there. So we're going to make room at the top for the new piece. And I guess what we can do is say while we can work our way up. Let height self height let's call it top, and then while, because we need to insert four things for the pieces, so we just need to make sure that there's enough room at the top plus 3. So while self rocks of top -7, right, if we look 7 down, is not equal to 0. Is that the way we want to do it? Oh, yeah, so it's actually while top self rocks len minus top. That distance down. Why is my brain broken? I'm just trying to look down by enough to see here, -7 is not equal to 0. Let's do it that way. Self rocks push 0. That way there will always be at least 7 entries, and we can start putting the rock at the top. So let's just slap a piece in there and print it out and see what the chamber looks like after we do that. Let mut bottom is equal to self rocks len -4. And then we can just say for p in piece self rocks of bottom is equal to P, bottom plus equals 1. So we're just slapping it in there, and then we'll see what it looks like. It failed. I got command error code 1. So let's see what happened here. Oh, bottom, yeah, bottom plus equals 1, right? Okay. Cargo run. We got a panic. It's 17 to track, but overflow at line 81. Oh, while top is greater than 0 and. Now it's 68. Oh, I thought we always had, oh, maybe I just need to throw in a couple more here. There we go. Okay, but it's at the wrong spot. So we actually want to make sure that we're at the height. We're at the correct height, which is going to be top. So bottom should be top plus 4. Can we do this? Top minus 7? No, because that's never going to change. We can do this. Let last is equal to self-prox len minus 7. And then just say while this last plus equals 1. All right, let's try that. Bacon. I'm just getting very hacky here. There we go. It's still in the wrong spot though. Why is the height wrong? We're miscalculating the height. Print len top. This should be 0. It is 0. So that means bottom starts at 4. It should go 4, 5, 6, 7. And for some reason, it's all the way up here. What the heck am I doing wrong here? This was supposed to be the easy part of the puzzle, right? 4, 5, 6, 7. Oh, I'm doing it backwards. That's why. Nope. So yeah, so the piece goes low to high and the bottom goes high to low. That's the problem. So the bottom of the piece has to start there, which means the top of the piece has to be, let's just do it this way. Let P row equals 4, while P row is greater than 4, P row minus equals 1, self-prox bottom equals P, bottom plus equals 1. Put a semi there, put a semi there, close this, and we're done. That's awkward. P. Piece of P row. Come on. And we don't want this. Yeah, we do want that. So computing. And now it doesn't show up at all. Oh, why are you P row greater than 4? P row greater than 0. Duh. Okay, it's still showing up too high. It should only be 3 above, not 4 above. There we go. Okay. So now we have to figure out how to make it drop. So we put it in here. This is what this looks like. That's good. I don't care about the blank rows at the top there. I'll live with those. We need to now figure out how to move it. And I don't want to slap it in here each time. I don't want to modify rocks until we have it locked in place. So let's do it this way. Let's make a loop. I'm going to start off by using the jet to move the piece left or right. So let jet is equal to self jets of self jet num. And then self jet num is equal to self jet num plus 1 mod self jet num. Oh, self jets left. Match jet. If it's a left. Oh, now we have to see if the piece can go left. Self. Oh, you know what we need to do is figure out what. Let's ensure that this is 7, because I want to calculate the bottom outside. There, that's 7 now. We can create the bottom here by saying, oops, self rocks len minus 4. And that way, as long as we maintain this 7 invariant, we'll calculate the bottom at the correct location. We can say if self can go left, give it the bottom that we want and the piece we're on. Then what we'll do is say for I in 0 dot dot 4, piece of I shifted by 1. Oops, it's the wrong way. That would have been bad. That's that. Otherwise, if it's right, if self can go right, bottom piece, and I'll write the can go right and can go left in a second. We'll do this, but shift it the other way, to the right. Okay, so that's the jet part of it, and now we need to do the drop part of it. Drop the piece by 1 if it can. Okay, so now if the bottom is greater than 0 and self can go down, can go to bottom minus 1 piece. Maybe I can make these all similar. Okay, so if it can go, then bottom minus equals 1. So we'll keep dropping it, else we'll break. And then we're done with the loop. Right? So this is basically move it left or right. And then this says move it down. And all we have to do is write these 3 functions now to determine where the piece needs to go. And now I want to insert the piece in the row just like we did here, except I don't want to just assign it. I need to make it an OR. And now, so the bottom is where it needs to go, and we work our way up. Okay. And then that'll be 1 drop, and then we can print it out and see if it looks right. It should look like, after it's done dropping, here. So it should be 2, 4, 1. So it will have looked like it didn't go left or right at all, but hopefully it will have done that. And then we'll do the second piece. Okay. So now we just need to write these little functions here. Self can go left. Self bottom usize piece is going to be a U84, and it just returns a bool. How hard could this be, right? It's basically this code and just checking to see if it will fit, right? Let mut p row equals 4, while p row is greater than 0, p row minus equals 1. Let's make this mutable. If self rocks bottom and p row, piece p row is not equal to 0, return false. Oh, we got shifted to the left. Oh, we need to check first. If piece P row and it's 80, 40, right? Because we only have 7 bits is not equal to 0, or that's not right. So if the leftmost bit is already on the edge, or if there's a rock that will intersect us, then we can't move left. And then can go right is the same thing, except the other direction. So piece P row of 1. But this is the same. Oh. It's not quite the same. Like that. And then this gets shifted the other way for can go right. All right, there we go. Can go left, can go right. And then we just need, say, can go 2. And this time we're not shifting the piece left or right, so we don't have to care about whether or not. But it's the same. It's almost the same logic, except we take this part out and we don't shift. Is that everything? What did I miss? It'll tell me. Piece. 3 more errors. Oh, I didn't return true on any of these. So if they all succeed, then they're all true. I'm going too fast, aren't I? Oh, right. And then if we don't have a good jet, all right, let's see what our first drop looks like. Oh, look at that. It dropped right to the right spot. What is this warning me about? Oh, because I'm not modifying bottom. I got to modify bottom. Right? Because as we do this, we have to look. Bottom plus equals 1. And now this is not needed. 106. I'm not using it. That's true. Okay, so there's one piece. Let's try dropping 2 pieces and see if the second piece ends up in the right spot. Is that right? That's in the right spot. Right? This is what we're looking for here. A new rock begins falling. Let's drop. Oh, we don't get to see the whole drop. We just get to see it, the final resting place. Okay. Let's try dropping 3. And does it end up there? I think it did. That's good news. All right, let's try dropping 4. Okay, I think we have it, right? Let's drop 5. And all we need to do is drop 2022, right? That ended up there. I'm going to keep doing this until we run out of test data. Just to be sure. Okay, that's good. Looks like there's one more. Yep. And one more after. Oh, there's a few more after that. Oh, there's a bunch. Okay. How many drops is this? It just says the next few. All right. I think I'm good. I think I'm good. Let's just try 4 and 0 dot dot. I don't know, 8. Oh, that's how many we have now. Let's do 10. Let's drop 1 and then draw. And it panicked. Perfect. Bad input. Oh, there's a new line. There's a new line. Okay, let's strip the new line. if self chamber jets of self chamber jet len -1 is equal to the new line, then self chamber jets pop. How's that? All right. Is this what we have here? Did I pick the right number of numbers? And then we have the new one falling, but I don't have that listed yet. All right. So I think we're there. Now, what do we need to know? How many units tall will the Tower of Rocks be after 2022? Okay. So we just need to drop 2022. I don't want to draw it because it'll be way too big, but I just do self chamber height. And then this should be 3068, right? And it's 0. Perfect. What? Why is it 0? Oh, because I did self chamber height. Oops. Part 1 height. 3068. Okay, I think we're good. Now let's use the real input. T 2022 17. And what do we get? We get 3219. Seems small, but okay. Hey, that's the right answer. Yay. All right. So I'm sure the next one is add 1,000,000 pieces. Ooh, 89. What are we doing here? Oh, I wonder if there's a smarter way to do this. Can I say for p in iter piece iter mut p 1? Well, let me do that because it is a copy. Yeah. So let's just do that here as well. And then just make sure we still get the right answer. What was it? 3219, right? 3219, and it took 7 milliseconds. All right. Code Monk says, yay, congratulations. Thank you. All right. And so Clippy's happy. We got the right answer, and we're going to commit these changes. Git status, git add source, git commit. -m 2022 day 17 part 1. There we go. All right, so part 2, continue to part 2. The elephants are not impressed by your simulation. They demand to know how tall the tower will be after whatever this number is, rocks have stopped. Oh. Only then will they feel confident enough to proceed through the cave. In the example above, the tower would be this many units tall. How tall will the tower be after this many rocks have stopped? All right, so obviously we're not going to calculate that much, right? What we're going to do instead is we're going to try to figure out how we can short-circuit the calculation. How can we short-circuit the calculation? First thing I'm going to do is I'm going to put this number in here. I don't know why the NeoVim's inserting that extra tab there. Const, what do we call it? We'll just call it a big number. This. Oops, that's not the number. We're going to copy-paste it so we don't get it wrong. And then I want to see how big it is. We can insert underscores. Okay. So it's 1 trillion. So what we need to do, we need to figure out what's a good state to save. Because what we can do is we can work our way through the drop. Because at some point, after this many times, it's going to cycle, right? After 1 trillion times, things are going to cycle. We're going to get repeated sequences of events. So I'm just looking here to see if there's anything we can do to try to. Well, the first 2 obvious pieces of state are the piece number that we're on and the jet number that we're on. Good Monk says, I'm going to leave. I'm going to spoil myself, still trying to figure out the solution part 2 myself. Okay, fair enough. Thank you. Thanks for hanging out. Hopefully you'll get it solved and you can come back. You'll get it solved much faster than me, and then you can come back and laugh at my solution. What was I saying? So piece num and jet num would be the two pieces of the state that we need. But I don't think that's good enough. We also need... somehow staving the state of the tower. But, I mean, it's obvious we don't need to know the stuff at the bottom of the tower. And I don't want to sit here and shift the entire tower down until we find a repeated... is there something else we can do? Maybe we can save like the top few rows. The pieces never repeat. I mean, sorry, the pieces never rotate. I was just thinking, well, can't save the top few rows because what if this long piece goes down this side here, right? Because this side looks like it's not getting any love. But the pieces don't rotate. So as soon as you have... And every piece is at least one wide, at least two wide. Oh, there is a tall one. Dang it. Yeah, I'm just thinking, so it's possible for a long piece to end up down this way. Although the jet will push it left and right. It won't, I'm surprised it didn't already. I'm gonna just try and see if this works, just for fun. And we'll run it obviously on the test input first. So part 2, we want to save the state, and we want to save the state. What do we need to remember? In order to calculate how high the tower is going to end up being, we need to let's say our state is the three pieces of information. State will be current piece number, current jet index, and I'll grab, I don't know, the first 8. Let's try grabbing the first 4 or top 4 rows of chamber. If we get a repeat, then we found a cycle. And the cycle needs to know delta height from previous cycle to this one, and then the delta drops. Drops. How many drops were needed to get to this height delta? Okay. So we need all that information. We also need to know the offset. How high the tower was when the cycle started. The first what's a good way to word this in English? I don't want to say when the cycle started, because the cycle starts the second time we find it. We want to say what the height of the tower was that we saved in the state, and then we find the second version of that, and that's going to be the height that we need, because we need to know that part as well. Cycle began for the first time, and then we offset drops. How many drops it took to get to offset height. And we should actually, these should be variable names. And that's what I'm going to call these guys here. Does that all make sense? I don't think I'm missing anything, but these problems are notoriously difficult to solve. All right. So if we're going to save state, we need to save our state. Our cycle is going to be, our state's going to be this. And then we need to save, so it's going to be a hash map that maps this state to these two variables. All right, so let's create a hash set. A hash map, sorry. Cycle finder. And we'll just put in here cycle finder. And then we'll just initialize it with all the zeros. So part 2, piece num, part 2 jet num. Oh, and then the 4 rows, the top 4 rows of the chamber, which are going to be 0 to start off with. Okay, so that makes that easy. And our offset height is going to be 0, and our offset drops is going to be 0. Okay. So now we're going to say, we'll loop. We'll say part 2, drop 1. We drop 1 piece, and now we get, we'll count our drops. Right? And now we'll get the current height. Now we want to grab the top, or the top 4, and just save those as a, I don't know, let's call it a shape. Chamber, part 2, rocks, height minus, height minus 1, yeah. So if height is less than 4, if we're grabbing the top 4, we need to at least get 4 entries in there. So height minus 1 shifted by 24, or part 2 rocks height minus 2 shifted by 16, or part 2 rocks height minus 3 shifted by 8, or part 2 rocks height minus 4. Right? And that'll give us our shape. And it's unknown, because I forgot to close the loop. It's a U8. Oh, it can't be a U8 as usize. There. Oh, that got messed up. It still doesn't like it. I have an infinite loop here, so I don't want to run. I don't want to save it and run. What am I missing here? Interpreted as a generic arbitrary. Okay. So I have to do that for each one of these. Like that. Although we have an extra pair of parens here. Okay, so that formatted. Hash map is not included, so let's import it. Oh, cycle finder insert. There we go. Okay. And that's, okay, let's make these U sizes, because everything else is a U size. And this is going to be, I just as a map state to, let's call it height and drops. Grapha says, I finally solved my day 8 part 2 problem and just about solved day 9 both parts. Nice. Good job. But man, what a mess of code. Yeah, that's what, that's what advent of code unfortunately encourages, right? Because you're just trying to get the answer. You want to get the answer. You don't care what your code looks like. I've seen, if you've seen like the speed solvers who start at midnight and do it, their code's a disaster. But it gets the answer, right? It's not something you would want to maintain. So I kind of take the opposite approach. I'm looking at this like, okay, this is something I want to be able to look at in the future and be able to understand. I don't solve for speed. I solve for fun. And part of the fun of programming is making code that I enjoy looking at later. So, but everybody has their own approach, right? If you get your answer and you're happy, go for it. If you get your answer and you're not happy with the way your code looks, well, scratch that itch. That's all I say. All right, so we have a shape now. We now want to insert it into the cycle finder if it doesn't already exist in there. So we can just say if let some entry is equal to cycle finder get, and then we're just going to do this, and this is going to be shape now. I got an extra set of parens there. Yep, okay, that looks better. So if we found a cycle, then we're done, right? We can break out of this loop and say, but we need to know all the information that we have. We need to save all the information that we have so we can print it out. Or you could just calculate it in here. Let me print out what we find, because I don't know what to do at this point. I just know that we have some information. So piece is R2 piece num. Mace the Blaze, thank you for the follow. Much appreciated. Wagafa says, yeah, me too. Oh, in terms of cleaning up the code. But day 9 had some complicated stuff with movements. I might have solved it in a bad way, but maybe I'll refactor it sometime. Oh, I see what you're saying, yeah. It's just the way you decided to solve it ended up causing the code to be unpleasant, not happy making, doesn't spark joy, I think is the current terminology. Jetnum. What am I doing? All right, so we print out the piece num, we can print out the jetnum. We can take a look at what the shape looks like. That's not a part 2 thing. And then we can find out what's in the entry. Println previous height is equal to this. And it's according to what I wrote up here, I'm going to put it in the 0. Entry.0. And then previous width, not width, drops is entry.1. And then I'm just going to break. NTL. There. Break. All right, that'll break out a loop, and then we'll see the unsolved. Okay, so hopefully it'll find a cycle. Oh, in order to find a cycle, we actually have to insert it. So we'll say cycle finder dot insert part 2 piece num, part 2 jet num shape, and I'm going to insert the value of our current drop, our current height, which we already have from up here, and our drops. Okay, I'm going to run it in outside of Bacon in case this ends up being an infinite loop, but let's see. And we're going to run it on the test input. Oh, I already switched that over. Okay. All right, so this is going to try to find a cycle. And I'm not using ouch yet, but I will. It found a cycle with this weird shape, whatever this shape is. I'm not going to print it out. It didn't take long, but this is just a test input. So maybe with the real input, it'll take longer. So now we just have to figure out how to use these numbers and the ouch number to figure out this number. All right, let's do it one step at a time because this is the only way my brain works. This is the drops until the loop starts. So let's write that down. Drops until start of loop, right? And then this is going to be height when the loop started. Right, so now we have these numbers. So println, we can determine there is an increase of this much for every this much drops. Let's actually calculate those out. Because that's the comment I had up above, right? So delta height, is it going to be height minus entry 0, and then let delta drops is equal to drops minus entry 1. And then we'll just put that in here. Delta height rows for every delta drops. Okay, this I can now run this in Bacon because we know it's not an infinite loop. And I'll be using ouch in a second because we're going to do some division. All right, so drops until start of loop. Take 17 drops before the loop starts. The height of the tower when the loop started was 29. So there's an increase of 53 rows for every 35 drops. Okay, so using that, let remaining drops, and this is where we're going to use the ouch value, minus the initial drops. Println, there are still remaining drops left to go. That's going to be a big number. Yep. Okay. So now we're going to divide by I don't know what to call it. Remaining drops divided by delta drops. And let mod, I can't call it mod, so I'll use m mod. Remaining drops mod delta drops. Okay, so given div drops will give us delta heights. So we can say, well, let's use these numbers to figure out what we need to do. Oh, mmod. All right, so this is how many heights we can get with 33 left over. So we can calculate that by saying let integral height is equal to the initial height plus the delta height times div. And we can just write that out. We can say after the height will reach integral height, but there are still, that's it, m mod drops left. Now we just have to drop those. The height will reach this, which is not quite that. Serge, thank you for the follow. Thank you. So we can calculate x per. We know this value, copy, paste, minus whatever we found here, which looks like it's less than, but it's very close, right? I'm getting close. There's 49 heights that we need out of 33 drops. So let's see if doing those 33 drops will do the trick. And we can just drop them for in 0.mod. Let's just call it leftover drops. This remaining drops, this is, yeah, leftover drops. And we'll call this drops height per drops. That way we multiply by, no, we multiply by height. We want to get height. Needed drops. That's what we'll call it. Needed drops. Okay. And then we'll just do a drop. So it's just part 2, drop 1. And now we can get the height, the new height, let final height is equal to chamber, oh, part 2 dot height. Oh, we need to know the current height, which we already have in height, in H, right? In height. Right here. Yes, so we have that information. And now println after mod more drops, we added call it leftover height to match leftover drops. We added leftover height rows. And, oh, because I changed the name, leftover drops. And I have to change them here too. After 33 more drops, we added 49 rows. Perfect, right? So now we just need to add these two numbers together, and we got the answer. So we just say return, create output of integral height plus leftover height. Oh, it knows that we can never get here. Okay, good. Oh, but I should have looked down here and seen that we have the answer. Right? I think that's the right number. That looks right. 151-428-571-4288. Perfect. Okay. Are we almost there? Dare we try the real input? It's a number of the similar scale. Oh, look at that. I'm so smart. SMRT. That was tough, figuring that out. That took a lot of brain power. I can't do this kind of stuff in my head, and that's why I had to do it one step at a time, just figuring out each individual piece of information until it all just came together. Wow. All right. Let me get rid of these prints because we don't need those for the final result. But I'm going to keep them in here because it's documentation. And that should clean that up. Good. And it's pretty fast. 16 tenths of a second, or sorry, 16 milliseconds. I'm going to try it in release mode and see. But that went faster than I thought it would go. Usually these things that take a long time, even when you work out how to do it, it still takes a long time. Okay, yeah, it's very fast. Let's make sure Clippy doesn't have any complaints. Git status, git commit. AM 2022, day 17, part 2. Okay. But now I have to go back. Return to my advent calendar because I'm missing day 16. Oh yeah, it looks like the volcano's getting ready to blow here, huh? The lava's starting to flow.